All right, so hope you all in the world are ready today. So this is a fantastic event, and I'm so pleased to have this opportunity to speak here. So thank you very much for the invitation. I hope you are having a great weekend. I know there was a hackathon yesterday involved. Hope many of you were doing that. I actually had family things happening yesterday, so I couldn't join you yesterday. But here today to talk about the powerful role of feedback in machine learning. And of course, feedback is important in all learning. Just like as children and as adults, we usually learn when we get feedback from things. And we're going to talk about that today in the context of machine learning and data science. So I am the principal data scientist and data science fellow at Booz Allen Hamilton, as well as being an executive advisor there. You can get the slides for this presentation at the link shown there. You'll also see that link again at the very end in case you miss it. But it's just kirkborne.net /DSGO 2020. So let's go. So the topics to be covered are these, the two most important things in data science, and then the talk about optimization and feedback loops in modeling and meta learning for machine learning. And then I'll spend most of the time talking about this problem called the cold start problem. That is, where do we begin when we really don't know what are the right features to choose, what's the right variables to select, all these kinds of problems where we don't really know where to start in machine learning, specifically unsupervised machine learning, but this even applies to supervised machine learning. And so my way of saying that is how to get out of this cold start problem is let the data become the model, and you'll see what I mean by that. So we're going to talk about these topics. And like I said, the very first one is the two most important things in data science. And I always tell people the two most important things are the data and the science. Now, some people will laugh at that and think it's a joke, but it's not a joke at all. It's actually extremely important because the data are the fundamental observational evidence, the objective truth against which we're testing the world with our models. And so that's all important. And of course, the science process itself is what makes it data science. If you're not doing a scientific process, you're just analyzing data, then you're doing data analysis. So data science is about doing science with data. That is testing the boundaries between positive and negative classes, true and false positives, true and false negatives, and not just finding that boundary once, but testing it, experimenting with it to see where's the optimum boundary. And specifically in recognizing that sometimes there's a different cost or risk associated with a false positive that's different from the cost or risk associated with a false negative. And that's a scientific process to experiment to find the optimal boundary in our supervised learning models, but also to find the optimal description of our data in the unsupervised learning models. So it's an iterative process, which we call science. So the feedback loop in science is all important, and that is what leads us to model optimization, the best model that we can find, not necessarily the best model in the universe, which would be the absolute best. Oftentimes, there's not enough resources or time to find the absolute best model. And this is specifically true when we're dealing with very large parameter spaces. I mean, most of us have hundreds, if not thousands, of features in our data sets. And an optimization in a feature space of that many variables is virtually an impossible problem. I mean, it's combinatorially infinite, basically. And so we don't find necessarily the universal optimal, but we find the best optimum, the best model within our limited time and resources. So anyway, we use this feedback loop that starts with observing our world through observation, and from those observations, we infer what we think how the world is behaving. We infer a model. We formulate a hypothesis to understand our world, and that's what a scientist does. I've been observing this and seeing this and collecting data on that, and I think this is the way it behaves. So I formulate a hypothesis, but it just doesn't stop there. It's a science process. So you design an experiment to test your hypothesis, and that experiment should be verifiable and repeatable by others. But you design this experiment, you run the experiment, you collect the data from the experiment to test your hypothesis. And more often than not, we need to refine our hypothesis, improve it. So there's a feedback loop and that learning how our model failed, how it doesn't actually replicate the real world. And this is always true. It better be true, because if you just do one and done, that is one model and stop, you're not doing science. All right, so the feedback loop is all important. So we revise and refine our hypothesis, and again, start again. We collect data to understand how did our model fail, why did it fail, under what conditions did it fail. And as we collect that more additional data, then we continue through this loop once again. Okay, the hypothesis formulation, experimental design, run the experiments, validation, verification, refine, and revising models. So I say both science and machine learning are experimental processes because they both focus on testing and iterating in order to fail fast, to learn fast. That's real data science. Again, it's about the data and the science. Excuse me. So the simplest definition I've ever seen of machine learning was probably one of the first definitions I ever saw when I started getting into machine learning about 20 plus years ago. My background is astrophysics. I spent many years working at NASA, the U.S. Space Agency, working on astronomy data systems, in addition to doing my own astrophysics research with astronomy data. And during those years, I was basically doing data analysis. And then I discovered this thing called data mining, as we called it in those days, or now what we call it basically data science. And machine learning was the mathematical tool to do that stuff. And so I said, what is this machine learning? That's an interesting phrase. And this definition I found puzzled me at first, and then over the years it's made complete sense to me. It's the set of mathematical algorithms that learn from experience. But what do I mean by experience? I mean basically past data, right? Training data. We learn the patterns from previous data in order to build correct models. So it's mathematical algorithms that learn from data. Okay, so first of all, it's mathematics. So the application of machine learning we call analytics or AI, but the math, the fundamental math of it is machine learning. And so training the algorithm with these past data gives us, for example, the first step in that scientific process of inferring what does it mean, inferring a model, then we design an experiment to test that model. So I always tell data scientists, if you want to interview with me, you better come prepared to tell me how you failed as a data scientist. I know many data scientists think in order to get a good job, you have to tell all about your success stories. And that's important. Yes, you have to have success stories. But success in any real world situation usually begins with failure. That is, building something wrong or not understanding it correctly. And I want to hear about that. I want to hear how did your models fail. What's more interesting about that, though, is there's actually a mathematical proof of what I just said, right? Because if you build a model, and let's say it has 80% accuracy. So 80% accuracy. How do you know that model is good enough? How do you know 80% is good enough? Until you build a second model with different parameters or different assumptions or different algorithms, and then see how accurate your second model is. And from your second model, if the accuracy improved, you know to improve in that improvement direction. That is, keep tuning your hyperparameter, so to speak, in the direction of improvement. If your second model is worse, that is, the accuracy is lower than 80%, then you know you're moving in the wrong direction, you turn around. So in mathematics, we call that finding the slope to a curve. In data science or machine learning, we call it gradient descent or gradient ascent, otherwise known as hill climbing. So you need to have two wrong models at least in order to know which direction to move in. Just like in mathematics, we know we need at least 2 points to find the slope of a curve. You cannot find the slope of a curve from a single data point. So if you have one model only and it's 80% accurate, you have no idea where to go until you build the second model. And so I want to hear about how you did that as a data scientist if you interview with me. But I want you, not even if you don't ever interview with me, I want you to be thinking about that as you build models, that you need to build at least 2 models in order to fail fast, basically to learn fast. So I heard this quote many years ago, and I think it applied to raising teenagers, which I've done a couple of, but it applies to life in general, as well as machine learning, and of the type that I've just described. Good judgment comes from experience, and experience comes from bad judgment. That is, if you want to build a really good model, you should sometimes start with a really ridiculous model and then tweak that and see how to move in a direction of better and better models. So start with a little bad judgment, or what I call it a little bit of machine unlearning. And we'll talk about that in a second. So I want to start with just an example of a cold start problem. Then I'm going to give more examples once you sort of understand this concept. And I'm going to use an example of clustering. And which basically, in cold start problem is basically how do you optimize a model from ground zero through meta learning and feedback in order to produce a really good working model. And so this story actually goes back to my days at NASA. And so it is a space science, a space astronomy story, but the focus here is not to teach you space astronomy this morning or this afternoon, wherever you are. The focus is on understanding the importance of meta learning and feedback for model optimization. So I think we probably all understand clustering, but here on this slide is a very long definition at the top of the screen here. The clustering is the process of partitioning set of data into subsets blah, blah, blah. Basically, what it says is grouping together similar items into one group and then separating the dissimilar items into other groups. So it's grouping things based upon their similar characteristics and patterns and behaviors, and such that the subsets in one group of items are different from the subsets of items in other groups. And so look at these little graphics I have here. They both are clustering examples, and they both start with the same input data set. These little geometric shapes of different colors. Excuse me. And as you can see, if you choose a different feature by which to cluster, you get different outcomes. So if you cluster the data by color, you get one set of clusters. If you cluster the data by shape, you get a different set of clusters. So you get actually different clusters, different outputs from the same input. So in traditional sort of mathematics, you learn about functions, right? Y equals f of x. You plug in x, you get a unique y. In this case, you plug in the same x and you get a different y. So this is part of the scientific process, is realizing there's some ambiguity in what we do. And the most successful data scientists are described by this term which they use in sort of behavioral psychology. They called tolerance for ambiguity. That is, you accept the fact that maybe there's no right answer. So how do we know what to do if they get different answers for the same set of clusters? In fact, if we had a huge set of data, not just these little points here, we wouldn't even know the correct number of clusters. We wouldn't know what features to use, especially since it leads to different clusters. How do you proceed from this? And once you do this, you may not have any understanding of the semantic meaning of those clusters. Sure, you clustered and separated your data, but what is the semantic meaning? And embedded in all of this and implicit in all of this is this word I've been using since the top of this slide, which is similarity, or distance. So similarity and distance metrics are things data scientists should know about. You should know that there's different ways to measure how things are similar or different. So maybe you've heard of the cosine similarity, or you heard of Euclidean distance, or Manhattan distance, or LP norm, or the Jacquard similarity. There's all kinds of different ways we measure similarity. And I'm pretty sure in most cases, depending on which choice of metric you use, again, you're going to end up with different clusters as the outcome. So what do we do here? Well, this is what I call the cold start problem. What do you know about the system? What do you do? The unfortunate side of the story is that this is the case for unsupervised learning. Unsupervised means you don't come in it with preconceived notions of what the classes are, because that would be called, if you did that, that would be called supervised learning. So how do you know if your clusters are good enough? Again, maybe the optimal, the universal maximum, so to speak, in an optimization function, but even if you can't find that, find the good enough solution. So one way you can define good enough is in a mathematical way, and that is in an objective way. And if you explain that to people, you say, this is my assumption of what I mean by good enough, they can challenge your assumption, your mathematical assumption, but they can't really challenge your outcome. You say, okay, this is the output if I make a certain assumption. And okay, so if people accept your assumption, then that is, you have to accept this is the objective outcome. So one objective metric, which again, it's subjective in the sense that you can choose different metrics, but it's objective because it can be measured. And that is, clusters are good enough if they're compact relative to their separation. That is, the individual clusters are small relative to the separation between them. Or another way to say it, if you could measure in some way the diameter or the radius of a cluster, that number must be small relative to the separation between clusters. And there's different ways of measuring that, and there's some links on this page, which you can come back to later if you get these slides. You get different ways of measuring compactness. And there's an equation there, which is one example. So excuse me. So back in my day at NASA, I had a couple summer interns. And one summer, I had a summer intern who was doing some data mining on stars in the galaxy to determine what are the most likely stars to have habitable planets. And I called this project Data Mining for ET. That is, data mining for extraterrestrials. Well, we weren't really doing that, but that was just a cool name for the project. And the student that was working with me, she was very excited to work on this project, and she was very excited to tell her fellow interns at NASA what she was working on. And the other interns were working on all kinds of different projects, engineering projects and science projects and even clerical projects, all kinds of things. And they asked her, so what is this data mining thing? So they invited me to give a talk on data mining. Excuse me. They invited me to give this lunchtime seminar to the summer interns, and again, a wide variety of students in the audience from different universities. And so I just chose a topic which was easy to explain, and that is clustering. So I gave this talk on clustering because everybody, even the little children, know how to cluster and sort things. So I figured if I give this talk on clustering, it'll be pretty straightforward for students with a strong math and science background, and even those in the room who did not have that. And I had this equation on the slide, and pretty much I had a slide that looked almost identical to this at that time. This was many years ago. And I didn't really say much about the equation. I just left it, and I moved on from there. So I talked about clustering, lots of examples in real life and so forth. And then about 2 weeks later, I get a phone call from one of the NASA chief scientists who invited me to his office to talk about some person in his office. Now, understand my context. I was a program manager on a contract. That is, I managed the people who were doing the work for NASA. And so one of the NASA scientists, the government clients in this case, my government customer, called me as the program manager, and said, "Hey, I got someone in my office I need to talk to you about." That was not always a good conversation. So I went there with a little fear and trepidation of what could be going wrong here, or what's happening. Maybe not wrong, but I wanted to know what was happening. So I went in there, and there was my colleague, that's NASA chief scientist, and he was a guy who was a pretty well-known guy in the field of space science, space physics. And he came before me and said, with a young man standing in front of next to him, and he said, "What did you tell these young people 2 weeks ago in that lunchtime seminar? This young man just solved a problem I've been working on for 25 years." And then my colleague, the space scientist, he started off sort of stern and serious, and then he sort of smiled, and all of a sudden I realized he was just playing with me. He was really excited to learn about this data mining thing because this young man took this idea of meta-learning and clustering, optimum clustering from small compared to separation. And he said, "Hey, I can maybe solve this problem that I'm working with my NASA mentor." This young man was a high school intern, actually. All the other interns were college interns. This guy was a high school intern, 16 years old. He solved a problem that the NASA chief scientist had worked on for 25 years. And he solved that problem using clustering. And what he did was he said, "Look, what if I try to cluster the data of things happening on the sun and things happening on Earth?" And so by clustering and adjusting the number of clusters, the choice of distance metric, the choice of features, I could find the tightest clustering between solar events and Earth events. Now, why would that matter? Well, the problem that this chief scientist was trying to solve was we see these solar events, these high energy solar energy events on the sun, and some hours or multiple hours later, those solar energetic particles reach Earth and cause all kinds of havoc. They destroy sometimes the communication satellites. They knock out the power grid, but they cause beautiful things like the northern lights or the southern lights, if you're familiar with Aurora Borealis or Aurora Australis. But they also cause cancer in airline crews who travel in airlines that fly over the poles of the world. And so even airlines restrict the number of hours that their crews can fly and during their careers over the poles. So there's a lot of serious impacts. And this NASA scientist has been working years to try to build a predictive model. What happens on the sun? When will it impact Earth? And this young man solved that problem. So as I said, he did meta-learning, even before I even told anybody about meta-learning. And he figured out how to use that equation, and I didn't even describe that equation. And he tried to find the tightest clusters between solar events and Earth events and said, when is there the strongest correlation? And that way, that will be sort of the model that helps to explain what's going on in the Sun-Earth system. But he didn't just do that. He did something extremely clever. He time shifted the data because he realized when something happened on the sun, it wasn't just several hours later that something happened on Earth. And so he decided to time shift the sun data by 0, 1, 2, 3, all the way up to 12 hours, and said, I want to find the tightest correlation between solar features, solar parameters, and Earth parameters. And some of those parameters are, for example, are the temperature, the speed, the density, the ionization, and different magnetic field strength. There's different things that the physicists would measure. And he clustered these things, and he found there was a minimum in this index. Remember I said you want to minimize the ratio of cluster size to cluster separation. And this one index he used, which was called the DBI index, he found that minimum sort of between 2 and 3 hours, 2 and 4 hours roughly, which is what the physicists already knew, but they really couldn't build a very good predictive model. And give some shout out to the physicists who were working on this. They were using extremely complex magnetohydrodynamic models with high performance computing with all kinds of very complex fluid dynamics and magnetic physics and all kinds of stuff in there. And this young man said, well, we just want a predictive model. Let's just build a predictive model. And so he found this minimum at just the right place that the physicists expected, and they now can actually use this process. So what this person did is he started from not really having any knowledge about the right number of clusters. So you see in this diagram, he tested 2 clusters, 3 clusters, and 4 clusters. And he tested, again, with these time shifts. And the minimum of all these curves was the 2-cluster model between 2 and 3 hours, or 2 and 4 hours. And it made sense that there was actually 2 clusters because there was actually 2 states on the sun, the highly active state and the quiet sun, as we call it, the active sun and the quiet sun. So there should be 2 states. There should be 2 clusters in sort of the sun-Earth interaction space. So he used some domain knowledge, which he had not very much of, but he was learning from his mentor. And he used the little bit of knowledge I gave them to actually solve a really complex problem pretty much from a cold start. Again, by using an objective function, this index which measures compactness relative to separation, he was able to find the optimal set of clusters given that assumption, and it turned out to be a pretty remarkable discovery. So I'm going to give you some more examples. Now, the ones I'm actually going to spend a little bit more time on are actually below the blue dotted line. So if you're looking at this slide that says more examples on the left, there's things below the blue dotted line that says, for example, K nearest neighbors, regression, clustering, which we already talked about, but I'll tell a little bit more about that. And then these initial weights and neural networks. I'll give you a little bit more details on those, but the ones above the blue line, I'm not going to spend too much time on, but I do want to draw them out and mention them here. And these are all examples of where the data becomes the model. So clustering is an example of unsupervised learning, and you have unsupervised learning and many things on this slide here. In fact, all of these things on this slide here. And what that means is basically you're building an explanatory model, which turned out in the case of that NASA intern to be actually a predictive model, not just explanatory. That is explaining the pattern in the data, and therefore the data itself becomes the model. If you want to know what the patterns are in the data, well, the patterns are in the data. That is, if you're doing pattern detection and pattern discovery, the data is the model. And so Bayes modeling, right? For example, you're looking at conditional probabilities of the different occurrence of different values for the different features in a complex system. So you build a Bayes network, a Bayes belief network. So those conditional probabilities of given X, what is the likelihood of Y? Those conditional probabilities, that whole collection of those is inferred from the data set. The data are the model. Markov modeling is a similar thing. It's essentially Bayes networks, but for sequences. Sequences can be time series. It can be a series of web clicks or customer behavior on a website. It could be cyber actor behavior on your network. So you can build predictive models or explanatory models even of what are the normal behaviors and natural behaviors of your customers or your cyber actors in order to look for those patterns, those personas, but also to identify anomalous behaviors that might be intruders or fraudsters or bad actors. So Markov modeling is basically Bayes modeling belief networks for sequences. Again, the data becomes the model because the conditional probability say, given this, what's the most likely next thing to happen? So you build a set of probabilities, a set of conditional probabilities, and that's the model. So a Markov model is nothing more than a collection of transition probabilities from A to B, where A and B are all the possible states of a system. So it's a complete matrix of transition probabilities. And as you learn that matrix, you can apply that model to do predictive analytics. Another example is association mining, sometimes used in recommender engines or lift modeling. That is, customers who bought product A will also likely purchase product B, given the history of other customers who purchased these products together. Again, the data becomes the model. Another example is network analysis or link analysis, which sometimes we see most prominently but never think about when we do searches on the internet. So search engines, specifically Google, uses a thing called PageRank, which is basically a model based to find the most central, most authoritative nodes in a network. So a network is basically edges between nodes, links between nodes, okay, relationships between elements in that network. So the network can be a knowledge graph like the internet, or it could be a product graph or a customer graph or anything. And so how do you find centrality in edges except from looking at the data? So the data becomes the model. So basically a search engine like Google works so successfully because they've analyzed all the links on the internet. They've analyzed the data. The data becomes the model. By knowing who links to what and who refers to which web pages when they want to refer someone to a particular topic, that information is captured. That's data. That information goes into the PageRank calculation, which is an mathematical algorithm based on data, and then the application is the search engine. So all these are examples where the data becomes the model. So let's do these little sample walkthroughs that I promised. So first, I'm going to clear my throat. So thank you. But keep in mind this one key point all the way through this, that the data becomes the model. So the first example is K nearest neighbors. Now, you may be familiar with K-means clustering, and this is a trick question on a lot of exams, especially when I was teaching these undergraduate courses at George Mason University for quite a few years. It would be like well, I wasn't trying to be a trick question, but I wanted to be sure my students understood that K-means clustering is a clustering algorithm, and K nearest neighbors is a classification algorithm. So normally think of classification as supervised learning, but wait, we're going to show something different here. Now, keeping in mind that data becomes the model, K nearest neighbors basically says if I have a new data point, which is represented by this circle, this black line with a gray center circle in the upper left plot, and I put it in the data space of other things that I have data about, which are the greens, the yellows, and the oranges here. I said, what is this new data point like? What kind of a behavior can I expect? If it's a customer, for example, and I put it into my product space and a plot of things that this customer purchased and what other customers have purchased, it lands in some place in this plot, in this data space. And I say, if I want to recommend something to this new customer, what kind of thing should I recommend? Well, let's look at the behaviors and interests of customers who are like this person. And so the way we do that is one way we can do this, I should say, is a K nearest neighbor algorithm. So we put that point in that space, and we look at the nearest neighbors and see what the majority of the neighbors, what category do they belong to, or in the case of marketing, which persona do the majority of the nearest neighbors belong to. So K nearest neighbors basically says, look at the nearest neighbors, and K is the number of nearest neighbors you're going to check. So in the example we show here, we use K is equal to 4. We look at the 4 nearest neighbors. So the rule of thumb sometimes that people say for the choice of K, the choice of the number of nearest neighbors you look at, the rule of thumb is sometimes like the square root of the number of items in your data set. So if you have 1 million customers, square root of 1 million is 1,000. So look at the nearest 1,000 customers and find the majority persona within those 1,000. So basically, you're using this distance metric as a way of explaining what this new thing is when you don't know anything about it. That's a cold start problem. We don't know anything about this customer yet except maybe a couple data points. Now we can put it into a persona because of the similarity that are close distance, I should say, to other personas. So one thing we're doing here is we're actually making an assumption, again, about that distance metric. What do I mean by nearest neighbor? So many times in our language as data scientists, we use words that have implicit meaning, and we better define what we mean by nearest. All right, not just that they're near to the circle, but how do you measure nearness? How do you measure distance metric? And remember, I said there are many different choices of distance metrics. And so how do you find the optimal one? Well, again, that's part of the cold start problem. How do I know what's the optimal choice of nearest neighbor? Do I use a Euclidean distance, Manhattan distance? Do I use a cosine similarity? Well, one thing you can do is you can test your hypothesis. All right, and this is sort of like traditional A/B testing in marketing. So suppose I start making offers to customers, and again, out of millions of customers, I'm making millions of A/B tests every single day. And I know a company that was doing this. They were doing 10 million A/B tests every single day. And you see how well those offers work. I mean, how often does the customer really select that product and buy it? Or how even just click on that product? How many times have they been even interested in that product? And so you can test your definition of nearness, that is your objective function, and see which ones work the best, which ones actually lead me to the best persona selection for this new customer based upon my nearest neighbor algorithm using a specific distance metric. And once you find that sort of optimal choice of metric, you've basically reached the point of optimizing your solution. Again, it's not necessarily the best solution, the absolute right solution, but you can optimize the solution from scratch using this feedback loop from changing the metric and seeing how well or how much worse the model becomes. Again, you need to build at least 2 models. At least, as I said, you need to build at least 2 wrong models to be successful as a data scientist. So it's a cold start problem using the distance metric as the thing that we're trying to objectify, trying to measure and optimize, but also at the same time using the data as the model because we're actually using the data points as the model. So this leads to an interesting conundrum because I just talked about k-nearest neighbors as a classification. We're classifying this persona or this new data point. We're doing a classification, and yet k-nearest neighbors is really unsupervised learning because we don't really have class labels on those data points. We just know where they live in data space. We haven't necessarily put any kind of label on them at all. You can do this, yeah, as a real supervised learning problem, for example, medical diagnosis or any kind of classification using k-nearest neighbors. With those colors that I just showed you, the green, yellow, and orange points actually possibly have real labels. Like if you're diagnosing someone with a headache, do they have a sleep disorder? Are they having eating disorder? Are they pregnant? I mean, so the different diagnoses based upon one single diagnosis, one single thing, the person has a headache. But look at their other symptoms and start seeing the combination of all their symptoms puts them closest to one or other of those different diagnoses. So you can do supervised learning. So anyway, this comes to this conundrum, which is you're using this algorithm for both supervised and unsupervised learning. And I love this quote that someone made, and the quote comes from this article. You can see the link there. That supervised and unsupervised machine learning can be seen as two different applications of the same general set of tools. They're really sort of like the yin and yang of data science. You can use them in two applications. And this is another example. This is a little cartoon of clustering, which I like to use a lot of times, especially when I'm teaching younger people in classroom settings. What do you mean by clustering? I show them this little thing, and I say, well, you already know how to do this, right? You can sort your toys and your things by color and by shape, and they understand that. And even when I have adult audiences, I say, think about this. Yeah, we can sort by color and shape, but even little children know how to cluster or separate their toys by function. That is, they know they can play ball with a spherical object like a ball, and they can build a castle or a fort or something with blocks. You can't really build a castle or a fort with spheres, with balls. And so they're already separating toys by function, by shape, and by color all the time. And so this is obviously an unsupervised learning thing, but once you know what these groups are and you can identify what is sort of the more optimal, and by optimal in this case might be which one gives me the most business value. There might be some way of measuring which ones lead to the best outcome. Again, that A/B testing thing. Which one leads to the best business value? And then from that point forward, you say, okay, these are the best clusters. This is the best way of separating the data, much like that NASA intern was doing. He said, what's the best way to do this modeling? Then it becomes supervised learning. So really, it's the yin and the yang of one algorithm that can be used in both ways. So another example is regression. Now, there's a little cartoon here. I hope you can see that it's animated. I can see it on my screen. I hope you can see. There's a whole bunch of data points, those blue data points, and there's a red line which is moving. And so this is actually a simulation of someone attempting to find the best fit line through these data. Now, before I go too much farther, let me just say, for linear regression, there is a closed form solution. In mathematics, there is an absolute way you can measure the slope and intercept of the best line through some data points, assuming that your metric is you want to minimize the sum of the squares, or in other words, the mean of the square deviation of all the data points from the line. So if you're doing mean square error regression and you're fitting a linear fit, a line, there's a closed form math solution. But maybe you're going to fit a curve, and that's a little bit more complicated. So let's assume that this person is fitting some kind of a curve, but it's a line in this case. But let's assume. So they start with, I don't know what the right answer is, so I'm going to start with a cold start solution. I'm going to say that the first model, which is going to be a really stupid model, and I'm a real big believer in starting with stupid models, because remember, you want to make two wrong models in order to proceed. So build a stupid model, then tweak it in a positive direction and see if it really did make it positive and by how much. And then you know if it improved it a little or a lot, you know how much to change hypertune your parameters to the next model. So they started with a model that said, suppose the curve has zero slope. Okay, so basically in this case, y equals 0. Okay, so if you can catch this thing right when it starts, the line is at y equals 0. They measure the mean square deviation of the points, and then they start iterating on that curve and they basically find that the mean squared error keeps going down as this curve increases in slope. And so they keep moving that line by changing its slope and its intercept to it ultimately minimizes the mean square error of the points, their deviations from the curve. Now, it doesn't show it here, but in most cases, you overshoot and then you got to come back. Okay, so that's that back propagation that happens, the back propagation of errors, the feedback loop. If you overshoot, then the mean square error starts increasing again. And then again, you use the slope of the curve, the error curve, to move back in the direction of less error, a little smaller error. So that's traditional sort of mean square error in regression. There's another type of optimization that happens with regression also, and that has to do with when we overfit or underfit our model. So if there's actually more structure in the data than a line, then you don't want to fit a line to it. So look at these panels here. These three panels have the same 5 data points. The little red X's are the same in all 3 panels. And someone fit a line through the 5 X's on the far left, and they make the assumption that it's a line. Okay, so it's a 2-parameter fit, a slope and an intercept, 2 parameters. And we would call this an underfit model because there's more structure in the data than our model fits. And in statistics, we call that a biased model, a high bias model, because there's more structure, there's more there than you're accounting for, you're taking into account. An overfit model is on the far right, where someone has fit 5 parameters to this data. That's called an overfit model. That is, the data has a lot of natural variance, and we're not taking that natural variance into account. So we're neither respecting the structure in the data nor the variance in the data when we choose one or the other of those 2 models. The best model, the just right model, which we call the Goldilocks model, it's just right, not too bad, not too fit, not too underfit, overfit. The just right model is a 3-parameter fit, which is a parabola in this case. So it captures the natural variance as well as respecting the structure in the data, or I should say respecting the natural variance while capturing the structure in the data. So how do we do that? Okay, so if you wanted to know which one of those, you could if you wanted to find the best fit line or the best fit 5-order polynomial to those 5 data points using the method I just described on the previous screen. That is to say, you can just minimize this mean squared error from whatever curve you choose. But how do you find the optimal curve? Well, we have this other metric which we call generalization error. So generalization error in machine learning basically says you need to have a holdout set, a validation set, a test set, something that was not used to train the model. And you measure the error in the test sample, the validation sample, and compare that with the error in the training sample. Now you can keep building model after model after model that eventually will go through every single data point in your model, and especially in regression, you can ultimately build a 1,000-order polynomial to go through 999 points or whatever. You can do that, sure, but you want better than that, right? You don't want a 1,000-parameter model for 1,000 data points, but the training can keep going down, 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 and you can reach tricked. But what you do is then you compare the mean square error against the holdout set, the data points that you didn't use in the training, and measure the difference, and that's called the generalization error. So generalization error is the feedback metric that we use to find the optimal model, the Goldilocks model, the just right model, to avoid underfitting and overfitting. So it's not the minimum of the generalization error, because look at the far left, you can see there's very little generalization error when you've underfit the model. So the trick is that you have to keep the training error going down as much as possible, as well as the test sample error going down as much as possible. But once the test sample and the training sample error starts diverging from one another, or in some cases, this test sample error starts increasing. For example, the example I mentioned where you overshoot and you fit a line that's on the wrong side of the data points, or you overshoot, the test error will start increasing again. You got to come back to that point where you find the optimal point. And there's a little bit of sort of objectivity or subjectivity in how you find that point, because again, it's not the minimum of the generalization error, and maybe not even necessarily the minimum of the test sample error, but anyway, it's a trial and error experience, and that's what we call science. So k-means clustering, I've already mentioned clustering, but I want to focus again on k-means. So k-means clustering is an example of piecewise regression. So piecewise regression we normally think of in a very traditional regression sense, in this case linear regression, where different groups of the data, you fit a different curve through the different groups because that's what the data says. Remember, the data becomes the model. So the blue line and the red line here are essentially a descriptive model of these data points. All right, fitting one single straight line doesn't make sense, and fitting a parabola or a higher order polynomial doesn't make sense, but fitting 2 pieces, that is 2 linear segments, does make sense. So k-means clustering is like that, where you're basically taking all these data points and you're saying, okay, I'm going to assume some of them belong to this group, and then another set belongs to this other group, and so on. Okay, so we're doing piecewise linear regression, and that's using that same language. These points belong to this group. Let's fit those. These data points belong to some other group. Let's fit those. And so you have a piecewise model. So k-means clustering is essentially a piecewise model. So I'll give a very trivial example here where I have 9 data points, and it's all one-dimensional data. So there's 9 data points, 4, 10, 12, 11, 2, 20, 25, 3, 3. So there's 9 data points there. And I'm going to assume there's 2 clusters. And I'm going to say, well, okay, so that's an assumption. Cold start problem. I don't know what the right number of clusters is. I don't even know what the centroids are. So the way we describe a cluster is excuse me, through a centroid. The way we describe a line is through a slope and an intercept. The way we describe a cluster is through a centroid. Okay, what's the mean value of the values in that cluster? That's how we define those pieces of the piecewise regression clustering. I don't know what those would be. Now, again, this is a very trivial example, but it works in high-dimensional spaces and very large data sets, of course. So I'm going to make one good assumption, k equals 2. You'll find out that's a good assumption in a few minutes. But I'm also going to make a really stupid assumption. I said, I don't know what the initial means are, so I'm going to assume these numbers. I'm going to assume the 2 means are 3 and 4. Well, you can look at the data and say, Kirk, you're making a really dumb mistake here. And that's the whole point. I want to make a really dumb cold start mistake and then show you how it can evolve into a really good outcome. So the way you do this is you make these initial assumptions of these 2 means, then you scan the data set, you scan through those 9 data points and assign the data points in the data to the clusters, those hypothetical clusters that have mean of 3 and 4. Then you end up with actually a real set of clusters. You can calculate the means of those. So those new means now become the new descriptions of the clusters, 2.5 and 16. There's 2 clusters, cluster 2.5, cluster 16. So you rescan the data, reassign the data points from that initial data set, those 9 data points, to those clusters 2.5 or 16, whichever one they're closest to. And then now you end up with a different set of clusters. So this is evolving. It's moving. It's like that line that's moving closer and closer to fitting the data points. So now the new means are 3 and 18. So we rescan the data, assigning data points to whether they're nearest to 3 or nearest to 18, and we get this set. And we recalculate the means, and now the means have changed to these other numbers, 4.75 and 19.6. We rescan the data set, put the data points into the clusters who are the closest to those means, and we get up with these 2 clusters. We recalculate the means of these clusters, and it's 7 and 25. We do that again, and it's the same number. Essentially, it's converged. That's the answer. If you keep doing this, it'll just stay 7 and 25 forever. In a real data world, you may have millions of data points, and they may not converge exactly. So you define a threshold. If it's within 1% change from the last cluster, then we'll just stop. 1%, 0.5%, 2%. You pick a number. And then you basically end up with 2 clusters. And if you go back and look at the original data set, you'll see that those 2 clusters, as shown near the bottom of the screen there, the cluster 2, 20 and 20, 20, 25 and 30, and the others, it really makes sense that there's 2 distinct groups here. And we started with a really pretty stupid initial assumption of the means and ended up with a pretty smart answer at the end. So the cold start problem led to a pretty smart answer. The last example I want to give, then I'll be finishing up, is artificial neural networks. So we're very familiar with artificial networks, right? They have all kinds of different pieces. And one piece are the nodes, and inputs, outputs, and the hidden layers. Another thing are the edges that connect those nodes. There's also this thing called the activation function, which basically says, given a given signal from one node, how much of that signal produces some kind of power output, so to speak, in the output layer. But there's another thing that's in here, and those are the edge weights. So the edge weights basically convey the information. It's basically the conveyor of information from the input to the output through all the layers, whether it's a simple neural network or a deep network. Those edges carry the weight. They carry the information. They convey the information of what makes a dog a dog. All right, so the edge weights basically said, given all these hidden layers and sort of the patterns in the data that correspond to those nodes in the hidden layer, you can communicate farther and further down the network whether it's a dog or not. But the real fundamental problem is we don't have no idea what the initial edge weights are. This is why it's a cold start problem. I call this basically cold start hell. we have no idea what those edge weights should be at the beginning, especially if you have a very complex network. If you've ever done any kind of computer vision on a deep network, you can have many tens or hundreds, perhaps even thousands of convolutional layers. You have no idea what those edge weights would be. So you're going to make a really smart decision. Oh, wait a minute. No, a really dumb decision. And this is what the undercover happens in these algorithms that you use. They actually assume something that you would consider very stupid, and I would consider very stupid, that all the weights are identical. All the weights are equal to 1, or all the weights are equal to some number, 0.1, or they pick a number. All the weights are identical, and all the edges. That's really dumb. But what happens, though, is we have this thing called backpropagation. Again, we make a really dumb, stupid model, and we're in cold start hell. We have no idea where to start. But we do one model, measure the error in that model, and then we basically figure out what proportion of the error was caused by different weights in the model, and that's determined by building multiple models and calculating the gradient, again, the slope, the rate of change of the error as you change a weight up or down. Same thing we talked about before. If we move the weight in one direction, it makes the model worse. Well, let's move the weight back in the other direction. So we can start adjusting all the weights, and that's essentially what neural networks are doing. It's basically recalculating those weights through the feedback loop, which we call backpropagation, which is determined by having multiple bad models, multiple wrong models, and ultimately leads to very accurate models and very accurate values for what those weights should be. And we know that artificial neural networks, especially deep networks, are some of the most accurate and most powerful methods for classification in the data mining world. So here's a supervised method, classification, artificial neural networks, a supervised learning method, which actually requires basically an unsupervised approach, which is we're going to figure out what those weights are, the optimal set of weights, through this backpropagation matrix. Now, that's sort of easy when it's sort of one-dimensional data, that's sort of that slope determination, gradient descent or hill climbing if we want to optimize accuracy, for example. When it's a very complex space, we have this thing called TensorFlow, which uses the tensor. So the tensor is the rate of change of the error with respect to all the parameters, both one at a time and in pairs and in triples. So all the ways that you can sort of find the covariance between the weight changes among all the parameters. And that's a good thing that the computer does that for us, because that's a very complicated problem. But the other cool thing that deep learning does that makes it different from regular machine learning is it actually finds the optimal set of features to classify a particular input to the correct output. Okay, so traditional machine learning, even traditional sort of shallow neural networks, the data scientist chooses the features to feed into the input nodes. In deep learning, the data itself becomes the model. Hence, once again, the data becomes the model. And the deep learning model not only finds through optimization and feedback and backpropagation and the TensorFlow boards, the tensor board, what are the correct weights, but also figures out what are the correct features to use, the optimal set of features. And that makes deep learning really special and different from traditional machine learning. Excuse me. So I've written about these problems in a blog here, not in the detail of the talk I've given here, but just sort of highlighting like 10 different examples of cold start problems in machine learning for data scientists. And the focus is always on this idea of building wrong models first to learn from them. Again, good experience comes from judgment. Good judgment comes from experience, and experience comes from bad judgment. So a little bit of machine unlearning and feedback and optimization can lead us to the optimal outcomes for our models. And so that feedback loop and that scientific process from the data, remember the two most important things are the data and the science. So let your data become the model and then use science to find the optimal solution. And that's it, folks. You can find links to all kinds of things that I am doing and my company is doing here on this page. You can download the slides here. And all these images on my slides are all clickable links, so you can just click on any of the images you see, like right here, and it will lead you to some web page associated with what you see there. So thank you all. It's really been great being here.
Well, thank you so much for that awesome keynote, Kirk. I know for a fact that everyone was just amazed at what you're saying. You had an awesome response throughout the chat. And, well, now we'd like to open up the room for a couple questions that people might have. So the way it's going to work is that the attendees will send questions to the chat. I'll receive them, and I'll forward them on to you. So, well, data scientists and attendees, you know what to do. Send your questions to the chat. So, Kirk, you ready to get started?
Yep, I had my drink. I'm Clear my throat, ready to go.
Awesome, awesome.
I have not
Okay,
been reading the chat questions. I didn't want to be distracted, so I'll leave that all up to you.
no, don't worry, we got you covered. We have a question coming in from Ilka. Question is, what are your thoughts on the problem that currently, even in published research, a lot of findings are irreproducible? What could we do to start overcoming this problem?
Well, for one thing, it's about documentation, right? We heard this for many years in our software engineering courses, our software practices. We have to document what we're doing, right? So it's not just documenting what parameters did I use in my model, but what are the assumptions. And so I go all the way back to that k nearest neighbors example. It's great that we use k nearest neighbors, but again, implicit in that word nearest is an assumption about what we mean by nearest. So we have to document our assumptions, document the parameters we use, the mathematical algorithms we use, and those things need to be openly available to the extent that you can do that. I mean, I'm not saying that you should just share openly your proprietary information. I'm not saying that, but things that are going to be used in a way that people need to be able to explain it and to be trusted, like trusted AI, explainable AI. We need to have that kind of documentation process. And so a lot of times documentation is just like words in a report that no one ever looks at. But I say tag your data, create tags, meta tags. Have the meta tags be carried with your model, be carried with your data. So there's sort of historical things, like for example, PMML, predictive modeling markup language, where they actually can have an XML language for basically creating meta tags to describe what goes into your model, what the assumptions are, and algorithms used, and things like that. So again, create some kind of documentation, preferably through meta tags, so it's easily searchable. It can be curated. You can search through all possible models. If you have like a database, a curated meta tags of models, then it makes it easier to reuse those models. Because the tag can also include when was this used, how was it used, who used it, in what use case. And not only that, you can have essentially a rating system, just like we go online and rate movies and rate books and we rate things. You can have a rating system. Yeah, I tried this model, but it sucked. Okay, so I give it a 1 star. Oh, I tried this model and it's fantastic. I give it a 5 star. You can look at people's ratings, and that helps you to understand whether to use this or not use this. So all these ways help us to get to the point where we're sharing enough information that it can be reusable.
Okay, wonderful. Well, Ilka, I hope your question has been answered. That was a very thorough answer. Thank you so much, Kirk.
Yeah, I give long answers to short questions. That's my problem.
That's almost always the best solution. We have another question coming in, this time from Diego. Diego asks, in business areas, do you think that problem solving can be done mostly applying supervised or unsupervised learning, and then the reinforcement learning is to be minimized?
Oh, I don't want to say one or the other. I think all of those, in the right circumstance, are valuable, right? I mean, certainly reinforcement learning has been proven immensely valuable in solving problems. Specifically, it's in some sense, reinforcement learning is sort of like an unsupervised learning problem, right? You have an optimization, you have an objective function that you're trying to optimize, and you have a set of rules about sort of like, here are the things we're going to do. So what makes it different from traditional unsupervised is you have those rules, but you still have some kind of objective measure of success. And so that reward and feedback is exactly what I'm talking about. So if you get down to supervised and unsupervised, again, it comes back to the business problem. I mean, you need both. I mean, I gave a whole lecture recently on just discovering models, actually predictive models, through unsupervised data exploration. Because once you do unsupervised exploring, you find patterns, that is trends and correlations and clusters and outliers and links and associations. You start finding these different patterns in the data, then you can start exploring those patterns and seeing which ones are predictive and which ones are prescriptive, which ones bring value, which ones don't. And so again, depending upon your use case, you could use any of those flavors of machine learning. And certainly supervised machine learning is essential when you are trying to classify or diagnose something where you know, is it A or B? Is this machine going to fail or not going to fail? So we have this whole field of predictive maintenance in industry related to that. Certainly in medical diagnoses, you better have some kind of supervised learning to diagnose correctly. So again, depending upon the problem, any one of those is valuable, and just focus on the business value creation. I always say focus on value creation first, then choose algorithms.
Wow, wonderful. I hope, Diego, that answered your question, and I'm pretty sure that answered it in full and then some more. We now have a question coming in from Nishant. The question is, from a recruiter's point of view, what are some of the key factors that you would like to see in a candidate's resume to shortlist them for an interview?
Oh boy. Well, first of all, any given job description is trying to find a specific person, I would assume, right? And so you want to be sure the person has the skills before you even proceed, right? You don't want to interview someone, they may be the best, nicest, most communicative person. They work well in teams, but they don't have any of the skills you're looking for. But on the other hand, maybe if you're building a team, you want to have the person who has those communication and team building skills, and maybe has very little of the coding skill. All right, very little of the mathematical skill. So again, if you're building a team, you want to make sure you fill out the full spectrum of the type of people that makes a successful team. And I often tell people what I call my sailing the 7 C's of data science success. So you may be familiar with the sailing the 7 C's. It's a very old metaphor from historical times, and it basically means exploring your world. I mean, it just sets you free to go explore your world. So we're exploring vast and endless seas of data. That's us. We're explorers. We're exploring vast and endless seas of data. And so you should be inspired and impassioned to explore data. So you should. So what I call the 7 C's are not oceans and seas, but the letter C: curiosity, creativity, communication, team building, collaboration. Consultative is one of those, which basically means listen and ask questions to your client, to your customer. You're building this for somebody. Unless you're a research scientist at a university, you're probably building it for yourself to write a paper. But in most cases, we're building for a client somewhere. And so listen to what they want. Don't walk in there and say, hey, I got this cool, really neat, deep convolutional network with the ReLU activation function and da-da-da-da-da. Their eyes are going to glaze over and not have any idea what you're talking about. But you're going to say, I'm going to be able to optimize the diagnosis and classification of this machine error or this customer error or this particular medical thing based upon the inputs and the patterns in the data. Then you got their attention. Forget the mathematical words and the coding words you use. So the person you're hiring, again, are they customer facing? Are they code facing? Are they data facing? Are they a team member? But I always say, again, coming back to that question, how do you recover from failure? Tell me examples for any of those people, for any job. Tell me about an experience. I've had those interviews in my life. They say, tell us about an experience where things didn't go well for you, and what did you do about it? And that shows levels of maturity that aren't captured in a resume. I mean, I had this terrible boss. He sucked, and everything I did, he hated, and I hated him. No, don't answer the question that way. I actually did have the boss from hell once, but no interview I ever went on, and went on many in the many decades. That never came up. Ever, because that's not me. I'm a positive guy. I want to keep moving forward. I want to see what did I learn from that experience? That's what's important to me. What did I learn from that experience? And I think that's what the recruiters should be asking is, what did you learn from that experience? Don't tell me the nitty gritty, dirty details. Tell me what did you learn from that? How did you grow from that? What made you better from that? And again, when you describe a model, if you want to get technical and describe machine learning, ask the exact same question. How did you do better from that model? How did you get out of that cold start hell?
Okay, awesome, wonderful. I think we have time for just one more question. This time from Sergey. Question is, how do you explain the time you spent on building the failing data models to executives?
That's a tough one. I've had that challenging conversation. I've learned how not to say it. For example, I've actually, in my earlier days, would say things like, we need to fail fast to learn fast, and the executive would slap right back at me and say, we're not here to fail. We're not here to fail. I don't want to hear that. Okay. So I try to talk about it from the point of view, again, of if they understand the mathematics of things, I will have that conversation about slopes, and you need more than one data point to. Okay. I also talk about how we learn from experience in the real world, right? I mean, Thomas Edison built the light bulb. Had 1,000 failures, but before he got it right, he said, no, I didn't fail 1,000 times. I learned 1,000 times how not to build a light bulb, invent one. Okay, so I talk about tactical failure versus strategic failure. And my father was military, so I know the language, right? Sometimes you have to lose the hill to win the battle. Sometimes you have to lose the battle to win the war, right? And so it's about tactical failure. So you learn from, you want to make little mistakes. That's what DevOps is all about. Machine learning ops, DevOps, data ops. those executives should know that language by now. Every executive in the world should know the language of DevOps by now. So you say you need to learn, you need to be agile. You want build small incremental projects, learn from those failures, learn from those iterations, and build on those learning experiences to do successful things. And the cool thing about building small projects like that, because you learn from the failure, and ultimately you'll have a success. And those small successes actually build culture in your company. When people see the success and the value that those analytics and data science and machine learning projects are bringing to the business, there's more investment that comes. There's more endorsement that comes. There's more support that comes across the organization at all levels. People say, "Hey, this is bringing value. Let's do more of this." So if you start with a big project, I always tell people, don't build a big battleship and never ever test whether your design works until 30 years from now when you finally launch it out at sea, the biggest battleship in the world, and then it sinks. Oops. Build those small incremental models. Some people call it the minimal viable product. I prefer to call it the minimal lovable product. This thing is bringing value to us. This little thing. Wow, I love this. Let's move on. Let's do more. How did you get that? Well, I had some failures along the way, but I learned how to make it better to bring value. Oh, yeah, let's do more of that.
Okay, Will, awesome. Thank you once again so much for the amazing keynote, Kirk. I think I can speak for everyone when they say that was wonderful.